Let's start with today's lecture. So, today we will be talking about bioceramics. So, we have primarily talked about polymers till now, because those are one of the most well studied class of materials for tissue engineering applications, especially for scaffolds. So, we will be talking about bioceramics today. So, this is a large class of inorganic non-metallic materials which is used in repairing and replacing skeletal and hard tissues such as hip joints, teeth, bone, etc. They can have antimicrobial activity and they are resistant to pH change, acid base solutions and high temperatures. They show better tissue responses than polymers and metals. So, I am talking about polymers which are synthetic and not present in your body. So, in case of ceramics, there are many ceramics which actually interact well with your body and integrate very nicely. They do not release any compounds into the human body which will cause foreign body responses. They are in general biocompatible to cells and can bind directly to bone. So, they fuse to bone to form one entity. So, they can be classified based on the source as natural and synthetic. So, natural would be coral derived apatites and eggshell derived apatites which have been studied. So, coral derived apatites have been studied for a long time. They are even FDA approved for using as bone substitutes. Eggshell derived apatite is something which is which people are interested in, and there has been some momentum towards understanding whether these can be used for bone tissue engineering and drug delivery applications. So, synthetic ceramics include alumina, zirconia and other calcium phosphates from different sources which have been used for bone tissue engineering applications. Based on tissue response, you can classify ceramics as bio-inert or bioactive. So, bio-inert is a ceramic which does not interact with the body's environment apart from causing the initial formation of a fibrous tissue. So, this fibrous tissue will coat the ceramic and further there is no other interaction. There is no aggressive foreign body response to these bio-inert materials. At the same time, they do not bond with the tissue, with the bone tissue. So, bioactive ceramics can actually bond between the host tissue and the implants. So, the example for bio-inert ceramics are alumina and zirconia. Bioactive ceramics interact with the body so that the tissue actually binds with the ceramic and there is an eventual incorporation of the implant into the body itself over a period of time. Ingrowth of bone can be achieved for these bioactive ceramics. So, the examples would be bioactive glasses which are non-resorbable, and you also have resorbable bioactive ceramics like calcium phosphates such as tricalcium phosphate and hydroxyapatite. So, coral based apatite is one of the older materials which was studied. So, these have interconnected pores with a skeleton which is similar to the cortical and spongy bones of your body. So, this has been used as a bone substitute and it was approved for use as bone substitute by FDA in 1992, and people have tried to use this. This is primarily calcium carbonate that can be transformed into hydroxyapatite using some chemical reactions. This shows better bone resorption in its original state. If it is used as calcium carbonate, it shows better bone resorption. Yeah. Bone resorption means it will be absorbed by your body. So, it gets replaced by the bone tissue, the actual bone tissue.
But the what do you call it, the stitches which are there which also get dissolved in the body, are those
resorbable, yes. Yeah. So, yeah, they are also called resorbable sutures. So,
like how does that work? Does the body kind of make a bone over it and then it will be dissolved, like how, because the stitches are fine, stitches can just dissolve into the skin, like the skin is already formed over there and healed. How will this work?
So, this also happens the same way. So, this is just like dissolving into the body, right. So, it gets absorbed by the body and new bone gets deposited in the place. So, depending on the rate of resorption and the rate of new bone formation, you will have replacement with the original tissue and so on. So, this coral based hydroxyapatite can be used as growth factor carriers, and it has been shown to be osteoconductive, and it shows excellent bone bonding capacity. So, in the sense that it can actually bind with the bone and form one entity. So, there are some terminologies which you should know: osteoconductive and osteoinductive. Osteoconductive is when new bone ingrowth is allowed, right. So, basically bones which are being formed can grow into the scaffold which you are placing. Osteoinductive is something which can trigger osteogenesis or new bone formation. Okay. So, osteoconductive materials are bioactive. Bioinert materials are not osteoconductive, they will just act as a barrier. Alumina is a bioinert material. It is actually a white powder and it can be shaped and compressed and sintered to form a ceramic which has very high density and strength. It also has very good corrosion resistance and biocompatibility. It also has high water resistance. It can be machined and polished. Because of this reason, it is used in the hip joints. So, if you remember some of the images I had shown of the hip joints when we talked about introduction. So, I would have shown some coating of ceramic on top in the ball and socket joints. So, these are usually alumina, and these have also been studied for artificial bones and dental implants and for artificial auditory ossicles and for orthopedic surgeries. So, there are different forms, different structures of alumina. The rhombohedral alpha alumina is the one which has been used for biomedical applications. These are very stable and cannot be dissolved easily even in strong acids and bases. So, most hip replacement joints are made of ultra high molecular weight polyethylene and metal, and what happens is when you have these polymer to metal contact, there can be wear debris. So, this wear debris can lead to osteolysis, which is the lysis of bone cells, and this can lead to loosening of prosthesis. So, people who were in biomaterials class, I would have talked about this. So, this is called aseptic loosening, and this will lead to the failure of the replacement itself, of the implant itself. So, to avoid this, people are trying to use ceramic on ceramic joints. So, where you have a ceramic coating on both the socket and the ball, thereby you have lesser wear debris. So, alumina has very good wear resistance. Because of this, people have tried to use alumina coating for such applications. So, the advantage is it has very high hardness and very low wear rate. It also has excellent biocompatibility, it does not cause any inflammatory responses, but the disadvantage is it is brittle and can cause cracks because of this. Zirconia is another ceramic which is also a white powder. This can be compressed and sintered to form a strong ceramic. So, the mechanical strength itself is better than alumina and its fracture toughness is also better. However, it does not have the same wear resistance as alumina. So, when you have friction, it is going to cause more of wear debris formed. There are different variants which have been used for zirconia implants. Phase transition can be done from metastable tetragonal grains to form a stable monoclinic phase. This causes an increase in volume and a reduction in compressive stress, which actually hinders from the crack from continuing. So, this provides its fracture toughness. So, when you have this phase transition, whatever crack is actually formed does not progress. So, only when the crack progresses, it is going to cause bigger failures. So, but this also decreases the mechanical strength of the material. So, people have tried to use partially stabilized zirconia, where yttria is doped along with zirconia and tried to use it as a stable variant of this zirconia ceramic. Presence of water can actually cause the phase transformation to happen more rapidly. This affects its in vivo applications. So, because of this, alumina has been used more extensively compared to zirconia. calcium sulphate is one of the most well studied and one of the earlier materials that was used. So, the first successful use of calcium sulphate was reported in 1892. So, it has been more than a century where people have been trying to use this. So, it is also called as gypsum or plaster of Paris. So, this was approved by FDA in 1996. The advantages are it has a structural similarity to bone, it is also osteoconductive, and it is very inexpensive, and it is available in different forms either as hard pellets or as injectable fluids. Thereby you can actually inject it into the site where you need to form a particular shape or structure. Calcium sulphate also has a crystalline structure onto which the bone capillaries and perivascular mesenchymal tissue can invade. So, this helps in integration with the body. It can be resorbed rapidly within 1 to 3 months. Resorption causes pores that can help in bone growth, bone ingrowth. Usually for bone ingrowth to happen you need to have pores, and this resorption can create these pores which can help in the bone ingrowth. However, this resorption rate is very fast. So, bone formation takes up to 4 months, and resorption of calcium sulphate can start within a month or so. So, this means it cannot actually be used for where you need new bone growth before this can be removed. So,
ideal state would be where both of these are balanced.
Yeah, it has to be comparable. So, you can have the resorption to be slower than new bone growth formation. It would provided it is not causing any negative effects. So, then it would not be a problem, you can have something there and it will still integrate well with your body. But if it is faster, then you have a problem. Okay. So, this is neither osteoinductive or osteogenic in the sense that it does not trigger new bone formation, it only helps in bone ingrowth. So, this can also cause redness and swelling at the site of implantation, which can cause discomfort and which can also cause serious pain, which would lead to failure of implants. Bioactive glass is a material, is a ceramic which was developed in 1970s, and originally silicates were coupled with other minerals which are present in your body like calcium, sodium oxide and hydrogen and phosphorus. The original bioglass, which is the 45S5 bioglass, basically contains 45% silica, 24.5% calcium oxide, 24.5% sodium oxide and 6% phosphorus pentoxide. So, this bioglass has been bioactive and it has been used for different applications. So, when exposed to aqueous solution or body fluids, what happens is the surface of this bioglass has the silica, calcium oxide and phosphorus pentoxide rich gel layer which is formed, and this gel layer is subsequently mineralized to form a hydroxycarbonate within a few hours of implantation. So, because of this it promotes bone ingrowth. So, it is biocompatible and osteoconductive. It can offer a porous structure which will promote resorption and bone ingrowth, and the porosity itself can be achieved with the way you fabricate the material. Okay. So, this does not induce any inflammatory response, and silica based bioglass is usually resorbed in about 6 months. Phosphate and borate based bioglasses have also been developed and they are also being studied. So, borate based bioglasses are easy to manufacture and they show faster degradation. However, this degradation can be altered by changing the composition of the material itself. Phosphate based bioglasses have controllable solubility, which makes them desirable for your applications because you can actually tailor the way the material gets resorbed. So, they show a strong bond to the bone and can withstand the stresses in the site of implantation. The disadvantage itself is it is quite brittle. All these bioglasses are quite brittle and have very low mechanical strength and decreased fracture resistance. So, this is a glass, right, it is a type of glass. So, it is going to be brittle. The problem with that is it does not mean you cannot use it. You cannot use it in load bearing applications, or you would have to judiciously use it for specific applications and specific sites. and you might have to fabricate it in a way that it will be suitable, or use it along with other materials to provide the desirable mechanical properties. Hydroxyapatite is the most commonly used material today, because hydroxyapatites are part of the apatite family, which are crystalline with a hexagonal lattice. So, they have a specific chemical formula which is Ca10 PO4 6 times OH twice. Okay. So, it is calcium to phosphorus ratio is 1.67. So, that is characteristic of hydroxyapatite. So, hydroxyapatite is what is present in your body. So, the mineral which is present in your bone and teeth is hydroxyapatite. So, because of this it is extremely biocompatible and does not cause any inflammatory response. So, you can use it for bone and teeth tissue engineering, dental tissue engineering without any issues. So, you can have a natural hydroxyapatite or synthetic hydroxyapatite. The natural hydroxyapatite is porous with various porosity depending on where it is being extracted from. So, if you are going to take hydroxyapatite from trabecular bone, it is going to have about 65% porosity with pores ranging from 100 to 200 micrometers in size. So, these pores helps in the osteoconductive property of hydroxyapatite. They have very slow resorption rate. So, they are going to be present in your body for a long period of time. They can actually be maintained in your body for up to 3 years, and this allows slow bone ingrowth and cell colonization. It makes sure that your implant is going to be there, and because it is hydroxyapatite which is present in your body, it is going to integrate very nicely with your body as well, right. So, it is going to bind with the bone and become a part of the new bone itself. It has very good mechanical properties with compression stresses which are close to 160 megapascals. So, which is good, but it is still not as good as your bone, right. Your bone compression stresses are usually in 10 to 30 gigapascals. So, this has very good properties. Synthetic and natural HA have been used. So, to get better properties, what people try to do is use hydroxyapatite along with tricalcium phosphate. So, this mixture which is called as biphasic calcium phosphate is preferred to using general hydroxyapatite or tricalcium phosphate independently. People have also tried using hydroxyapatite collagen composites, which is what your bone's ECM is, right. So, your bone's ECM primarily contains collagen and hydroxyapatite. So, this enhances osteoblast differentiation and promotes osteogenesis, new bone formation improves. So, the ductile properties of collagen actually make sure it can be prepared in the shapes, and it provides the mechanical properties which are desirable for the bone itself. So, you can actually prepare these nano composites where hydroxyapatite nanoparticles are prepared and dispersed in collagen, thereby you get structures which are very close to what your bone tissue would be. Calcium phosphate cements were invented in 1986 and this was approved for non-load bearing bone defect treatment in 1996. These are a bioresorbable material which can stay in your body for about 2 years. So, these consist of a calcium phosphate powder which is mixed with a liquid, and there is an isothermal reaction leading to the hardening of this in 15 minutes to about 80 minutes. So, this is what is used in your dental fillings and so on. So, the result after the reaction it results in the formation of nanocrystalline hydroxyapatite which makes the calcium phosphate cements osteoconductive. So, the advantage of using these is it can actually be used to fill gaps and cavities, and because it is a paste, it will actually fill the it will take the shape of the cavity in which you have used it. So, injectable cements have also been used for vertebroplasty and kyphoplasty, which is basically injuries to your spinal bones, okay, and your disc problems. Like if you have a compression fracture of your spine, then these kinds of cements have been used so that it can be used for healing the fracture. So, These are brittle, and the clinical outcome is not better than that of methyl methacrylate. Because of this, people still sometimes prefer to use methyl methacrylate, PMMA kind of alternatives instead of cements. Beta tricalcium phosphate is the most commonly used bone substitute. It is a pure hexagonal crystal structure with high biocompatibility and bioresorbability. The porosity regulates the osteoconductivity of this material, and the resorption is actually slower than other calcium phosphates. However, it gets completely resorbed in about 13 to 20 weeks. This is faster than hydroxyapatite though. Reports suggest that they have ability to influence angiogenesis as well. So, bone is actually a very highly vascular tissue. So, it has a lot of blood vessels, and it is important to create a bone substitute which would have these vascular networks. So, beta tricalcium phosphate has indicated that it can influence how the bone, how the angiogenesis happens. So, some of the commercial materials which use beta tricalcium phosphate are orthografts and Ospirion. So, these are used for bone replacements and regeneration. The biphasic calcium phosphate is a combination of hydroxyapatite and beta tricalcium phosphate. As I said, it is preferred to HA and beta tricalcium phosphate being used independently. So, this has the advantages of both these materials. So, it is highly osteoconductive, biocompatible, it is safe and non-allergic. It also promotes bone formation, new bone formation. So, in the sense it is osteoinductive. It enables faster and higher bone ingrowth rate compared to hydroxyapatite alone. It offers better mechanical properties than beta tricalcium phosphate alone. So, the strength is still lower than the cortical bone's compression strength. So, optimizing this to get desirable mechanical properties is always a challenge. So, we looked at different fabrication techniques for scaffolds earlier. So, the techniques which we looked at were all primarily for polymers, right. So, those are scaffolds which we can prepare from polymers or different types of polymers. So, similarly for ceramics, there are different techniques which can be employed, and we will just quickly go through some of the techniques. So, one of the most common techniques is foaming method. So, as I said, porosity is crucial for ceramics because that is what will regulate osteoconductivity. So, bone ingrowth will happen when you have a porous structure. So, the techniques which we will be looking at will have ability to create these porous structures. So, foaming method is capable of producing highly porous ceramics with pores which can range from 20 micrometers to up to 1 to 2 millimeters. So, what happens here is you disperse a gas in the form of bubbles into a ceramic suspension or colloidal solutions, and this is done by incorporating an external gas by mechanical frothing or by injection of a stream of gas along with this suspension, or introduction of an aerosol propellant. You can also have create evolution of gas in situ, either through in situ polymerization or techniques like that. So, this suspension is then solidified, and eventually the gases are released, the foaming agent is released, thereby creating porous structures. So, this is similar to one of the techniques which we looked at for polymers. So, where again you used things like ammonium carbonate, where carbon dioxide can come out, creating the pores. So, the disadvantage is it is difficult to achieve high pore interconnectivity, and also there is a non-porous external surface. So, the pores are present only in the inside, and it might not be present on the surface, which can cause problems. You need to have a porous surface for the bone ingrowth to be better and for cell infiltration to happen. Amongst these foaming methods, there are a few different types. So, H2O2 foaming is one of the more commonly studied and a simpler technique to use. So, what is done here is the ceramic powder is mixed with an aqueous solution of H2O2, where H2O2 is the foaming agent. So, the mixture is cast into molds and stored in an oven at 60 degrees Celsius. The H2O2 hydrogen peroxide decomposes and oxygen is released in the form of bubbles in the slurry, which causes the foaming process. And as these bubbles come out, you create the pores, and finally the sample is sintered, and the percentage porosity and the pore size can be modulated by using different concentrations of H2O2 and so on. The pores are interconnected only in a laminar manner, which results in poor interconnection in the direction which is perpendicular to the laminae. So, it can only be connected in one direction. So, another technique which is used, which is an eco-friendly technique, is the starch consolidation technique. So, corn, rice or potato derived starch granules are used as pore formers and binders. So, what is done is the starch granules, ceramic powder and water are mixed to form a suspension, and the suspension is continuously stirred and maintained at 60 to 80 degrees Celsius, and finally these are cast where the starch starts swelling, because starch can absorb a lot of water and forms a gel like material. Then it is thermally treated. So, in the sense it is heated to burn out the organic phase and sinter the ceramic phase, and because of the starch granules which occupy the cavities in between where the ceramic is sintered, you will have pores which are formed. However, the pores are not interconnected in this case, because only the starch granules occupy the pores, and there is no way to create interconnected pores. So, sponge replica method is the most common method which is used for commercial materials. So, what you see here are commercial bone grafts which are manufactured using sponge replica method. So, the technique itself was patented in 1963, and this has been quite popular and very effective. So, what you do is you basically impregnate an open cell porous template with a slurry of ceramic powder and a binding agent. So, you first create a template, the shape in which you want to create the scaffold, and this is usually made out of some natural or synthetic polymer, and you then load it along with the ceramic slurry which is present along with it, and the sponge is squeezed to remove any excess slurry, and the ceramic is used to coat the sponge. The struts and the curves which are present are coated with the ceramic as a thin layer, and then this is dried, and the coated template is pyrolyzed to remove the sacrificial template. So, now you have only the ceramic which is remaining. So, you create a positive mold. So, whatever mold you created, you have the exact shape in the form of a ceramic. So, the ceramic coating is sintered at high temperature, so that you get the porous ceramic with the same architecture, and during sintering the sacrificial template is lost. So, the most crucial step in this sponge replica method is to get uniform coating on the polymeric structure, because if you have ununiform coating, then you are not going to reproduce the same structure. So, the factors which influence this are the rheology of the material and how well this suspension can adhere to the struts in the sacrificial template. The rheology is crucial because it needs to be, the suspension needs to be sufficiently fluid for it to allow penetration. It needs to reach all the areas of the template so that it can coat it completely. At the same time, it needs to be sufficiently viscous so that it does not just drain off after coating. So, after coating it needs to stick there and remain there. So, that will happen only if you have the right viscosity. So, the limitation with this method is you may not get desirable mechanical properties, you would get something which is slightly weak. So, other than these techniques, you also have the solid freeform fabrication techniques. So, these are broadly called as the rapid prototyping techniques. So, these are moldless technologies where people use layer by layer deposition using computer generated 3D models. There are different strategies, stereolithography, selective laser sintering and powder based 3D printing are the most common ones which have been used, and all of them seem to have their own advantages and disadvantages. So, I am not going to go into details of the advantages and disadvantages, but you can go through these review articles. I think I have already uploaded them, I am not sure, but if not I will upload them today. So, these review articles and book chapters actually give you enough information about ceramics, and I have given you an overview of what ceramics are. So, with this we come to the end of the different materials which are used as scaffolds. So, we will talk about cells, the cell sources, cell types which can be used, and also tissue homeostasis regarding cell adhesion, migration, proliferation and so on in the next few classes. Okay. So, thank you.